Hello, good morning, everyone. A pleasure to be here, and thank you, Reza, for such a wonderful introduction, which is very hard to live to this introduction. But anyway, so actually I'm going to talk about something you mentioned earlier about the impact that AI is starting to have in many, many other computer science disciplines. And in this particular case is that about how to accelerate the system research with AI. We call this direction or this effort AI-driven research for systems, or Adress for short. And here is a story. Now, AI and machine learning have been used to improve systems for a long time. I think this is a talk from Jeff Dean, which pioneered this effort long time ago. I think this was 2018, the NeoRIPS talk. And since then, many people try to apply AI machine learning for solving different problems in systems. Everything for improving the schedulers for different systems, query optimizations, network classifiers, and more. So what is different now? So just to compare, it's like what I think we are seeing a phase change from the black box to white box, which is actually pretty obvious in retrospect. So in the past, what machine learning and AI was used for is to either tune the knobs of the system to perform better for certain workloads, or to replace some of the components of the system with some models, like classifier or query optimizers. You train a model to do that kind of function. This is kind of either you look at the system as a black box, or you replace a subcomponent of the system with a black box. However, now we are seeing this kind of white box, which I think is a fundamental shift, because you are going to operate on the system code. So you operate the code itself. And what I'm going to focus in this particular case about system is on performance improvements. It's an easier problem. And what was generated this kind of line of work, which is very recent. So it was this paper, AlphaEvolve, which was published May last year, so 9 months ago. And then it was, it's FunSearch. It's a previous paper. This is AlphaEvolve, the one I mentioned to you. And they were showing that you can use this kind of evolutionary approaches based on large language model to solve some problems in algorithms and even kind of systems. And then OpenEvolve is an open source version of AlphaEvolve, which came a few weeks after that. And since then, there are many other works. Japa is one effort coming from our lab from Berkeley. And obviously, you have code assistants, which I assume everyone is using it these days. So this is what happens. And then we decided, actually, in this last summer, in our lab, with the students who are not at the internship, to run this kind of experiments and efforts. So what we wanted, at least I wanted to see, is that because typically what you do, you develop these frameworks and so forth, and you have a bunch of benchmarks, and you are going to see how good are on benchmarks. But how good are they in real life, right? So what we took, like basically say it was like, again, a dozen or a few more the students, and I asked that each of them to apply it on their kind of topic of research, on their research projects or some of their previous research projects. So there are around 12. And as you can see on the left-hand side, and I'm not going to go to explain each of them, but these are papers, the project which are published in top conferences in the systems. Some of them, they are submitted papers, and some of them are kind of new, right? It's like ongoing projects. And they apply this with OpenEvolve, and the results are surprisingly good because, at least from my perspective, because in 10 out of 12 cases, they exceeded the SOTA, right? The best results. And it also was quite cheap, right? The final runs of a few tens of bucks, okay? So it's quite impressive, right? Like that's why it was a successful experiment. And this, again, this is not just a benchmark. It's just people applying these tools on their own research. So how is, let me take a step back and talk a bit more about what is in general the research process in systems and actually in many disciplines. So first of all, you come with a problem. What problem you are working on? What problems you want to solve, right? Then what you do, you put together an evaluation framework, experimental. You design the experiment to show about how your solution you are going to develop for this problem is going to solve the problem, right? And then you start coming up with solutions and you evaluate them using this evaluation framework or experimental design you did. And you iterate until you get good enough solutions. And then if you are a student, you are going to publish a paper, right? That's what you are going to do. So what we are going to have to focus is on these cycles. We are not going to use AI to come up with the problems. You are not going to use AI to design the evaluation framework. You are not going to use AI. You can use AI a bit for writing the papers. Why? Because we want really to, again, this is about research, so we want to push the Pareto frontier of the results, right? We don't want just to do AI end-to-end, and then, of course, you can, I think, the standard there will be, can I get the paper accepted by a conference? But that doesn't really push Pareto frontier. It just, who needs most, another mediocre paper, right, in this world. So that's kind of thing. And how now? And how these are working. Okay, so it's working the following ways. You have the solution generator. It's like you may assume it's a large language model. And outside, again, you have the problem formulation and evaluation framework. And you use that, I'll be more explicit later, I'll give an example, to create a prompt, to describe the problem and give all the information to the large language model, which is going to generate a solution by modifying the code. Then you are going to evaluate it, you are going to get a score for the solution, and you are going to store that solution and the score in a program database, and then you are going to select some of the solutions to add for the next prompt to add more information to iterate to get better solution, right? So this is kind of internal loop, and basically you can have the researcher external loop looking at the results and adapting parameters, maybe changing the system prompt and something like that. So here is an example. The example is expert parallel load balancing. How many of you are familiar with this problem? Okay, so this is very simple. Mixture of experts. You have right now these models, or basically all the top models, a mixture of experts. They have a lot of experts, smaller models. So when an attacker comes, you are going to route to one or more of these experts, right? And it's very dynamic process for every token, and even for every token and every layer, you can route through the different experts. And these are large models, so you need to assign experts to multiple GPUs. You don't have one GPU. And obviously, the question here is about how you load balance, right? How you make sure that each GPU is highly utilized, because this will improve the throughput. Improves the throughput, reduces the cost. Again, this is for inference, just to be very clear. Okay? And some experts are going to be very popular. You may need to have multiple replica of the same expert running on different GPUs. Some experts will be much lower utilized, so you can have a bunch of experts on the same GPU, right? That's what it is. So here is how this is working, okay? So the prompt basically describes the problem. You can see it describes the problem, and then you describe what are the goals. So the goals are twofold. I think it was here, which I didn't say. There are two metrics. And one metric is balancing, how balanced it is. The more balanced, the more you can push the throughput, lower the cost. The second one, because I told you this is a very dynamic process, then you need to reassign the experts pretty frequently. So the speed in which you do reassignment is another metric for how good it's your solution, okay? So it's again, you are going to say what is the problem, you are going to say what are the objectives, right? And then you are also going to provide the code. In this code, how you simulate this is simulator, right? Sorry, how do we evaluate? In many of these problems, you have a simulator, which is a proxy of the real system. And this is what we do in research because it's faster, cheaper, and everything, right? So most cases, you already have the simulator. So you provide the simulator, and the simulator, you say, okay, this is a code which is doing load balancing. This is a code you have to evolve, to change, to become better, okay? And the LLM will update will generate the solution, which means to propose a better code to optimize your problem. Then you are going to evaluate. You are going, in this case, to provide the average balancing factor and average time to rebalance. And you are going to store the solutions in this database. And then for the next iteration, you are going to select some solution. You are going to select one solution, which is a parent, to evolve it in a new solution, and you are going to provide, in this case, some other solution which you call inspiration. And typically you provide, in this particular case, 2 solutions, which are the best solutions so far in terms of scores you created, and 5 random ones, more or less, to improve the diversity, right? Okay, so basically add to the problem saying, hey, you need to evolve this program, and these are some other examples of solutions to the problem, and these are their scores. Okay? So this is pretty much it. Oh, and you have also this concept of islands. For diversity, you have different group of solutions. You evolve in parallel, and then you can migrate the best solution from time to time between islands. Okay? So that's what it is. This is about the island, which I just mentioned. So what are the results? So here are the results. So we did that on the DeepSeek R1, right? So this was happening in June last year. So, DeepSeek R1 was in February released. And we had a baseline implementation of DeepSeek for this expert load balancing. And we also had access to an internal implementation. I have a student who was doing, working there on a postdoc, actually. And the results were the following. The balance factor, and we have new results which are better than this, but this was at that time. It was like the same as the best as a solution out there in the open source, and is an internal solution. But the rebalancing algorithm's runtime was hundreds of times faster than the OSS implementation. Not only that, but it was 1 order of magnitude faster than the highly optimized proprietary implementation. And there is no contamination here, right? Because this was developed after the DeepSeek was trained, and it was not publicly available, the code. Okay? I'll tell you a little bit more what I think. And by the way, on the top of that, the code was much easier actually to understand because the proprietary implementation has a lot of constants every line. So it was very hard to understand. This was much easier actually. And it was cheap, right? The final run, 5 hours, 300 iterations. This is 300 LLM calls. And it was a combination at that time between Gemini 2.5 Flash and Flashlight. So that's kind of the results. And this is what happens. This is evolution, right? If you look about the evolution, you see you have different techniques are discovered at different time of the evolution. The number of iterations on the x-axis, on the y-axis is a combined score between these 2 balancing factor and time, how long it takes to rebalance. And then, it's like some different vectorization techniques, and then you have a breakthrough. You discover a zigzag pattern to do the load balancing. Okay. Now, since then, there are more evolutionary systems. It's another one, ShinaEvolve, which is derived from OpenEvolve, and it's doing every 10 solutions, summarizes each solution, provides aggregates insight, provides recommendation for the next steps. Japa is something we develop at Berkeley. Matei is going to talk about this later in the day. It can handle multiple results independently, select solutions on Pareto frontier, and can write the entire programs. And AlphaEvolve also, dynamically adjust between exploration and exploitation, another system we built there. I'm not going to go through all the numbers here, but this is some experiments using OpenEvolve and now ShinaEvolve using GPT-5 and Gemini 3, all the combinations, and for I think 7 problems or 8 problems, and then with in bold numbers are the ones which are the best, right? And in all cases you have 100 iterations. This is Japa, and this is AlphaEvolve. So you can see, we improve the results and so forth. But I think that's, and it's, I can tell you, probably there will be hundreds of improvements of this kind of OpenEvolve being designed right now. So you'll see a lot of progress in this space. We also have a Leaderboard trying to track the progress in this space. So please, you submit your own problems if you want to try it, and things like that. Okay, so now I told you about what we tried, kind of what the results, where we are. So now let me tell you about some lessons we learned in the process, because I think this is always interesting. So the first lesson is like less is more and more is less. What I mean by that? It's like one of the questions is about how the baseline, when you start the problem, how strong is the baseline, right? You can start from a SOTA or from a weak baseline. For instance, you have an algorithm, you have the best algorithm, so you have a greedy algorithm, which is a baseline simpler. You may think that starting from the SOTA, from the best algorithms, no algorithms is the best thing to do, but it's not always the case. Sometimes a weak baseline can lead to better solutions, okay? And why is that? Because sometimes if you start from a strong baseline, that kind of be a local minima. And sometimes it's hard to get out of that minima, while if you start from a weak baseline, you avoid that local minima. Okay? So one of the strategy, because it's also to use to have different runs, the natural strategy to have a different runs with different baselines. Right? Strong and weak. Now, the other thing you are going to see is about hints, okay? How much you are going to tell the system about the problem, right? Just imagine that you are going to work with a student, or you are going to mentor someone, right? A junior engineer. You tell that engineer, do X, and by the way, these are the best practices I would suggest you to use these solutions and so forth, these libraries and everything, right? This is what you're doing. Well, it turns out, and this is what it's intuitively every one of us will do, right? We give advice how to do things. Because you think you have more experience and you provide some shortcuts, you accelerate the progress of that person. It turns out that it's not always the case. And it's like, because what you do, and in this case also why you want to give hints, is you want to restrict the search space, so to get faster results, and hopefully better results. But the fewer hints provides also more freedom. Maybe sometimes, the student comes with a solution you haven't heard about, you haven't thought about, right? So it's kind of a balance here. Or, like you have a very brilliant junior engineer, which come with just better solutions than you thought about, or you consider, okay? And here there are also some kind of best practices also. So if you have hints, because again, you have ideas about the problem and it's your problem, don't use all hints at once, right? To reduce. So basically, try to provide less hints, which kind of to increase the exploration early on, and then you may get in kind of local minima. Maybe you can provide more hints then to get it out of the local minima, right? So that's kind of one strategy. Start with fewer hints and then add more hints as the process becomes more, as the solution starts to improve more and more. The last one, which is related, is to restrict access to high-level library APIs. If you restrict access to high-level APIs, you can lead to better solution. It's again, you have high-level APIs, you have faster evolution. But you are going to be, you are going only to be as efficient as that API. So here is an example, like EPLB. When we provide, you are tempted, provide, say, use PyTorch API, but then it replaces a custom operator with a PyTorch primitive. If you don't give that API, you say don't use that API, actually it's going to derive the code for that operator, custom operator, and that code will be sometimes much faster, okay? So that's what. The other very important lesson, which is probably very obvious, is a solution is only as good as the evaluator, okay? A flawed evaluator was a primary cause of flawed solution. You need to prevent overfitting, right? Typically when you have simulators, you have a bunch of traces, you are going to evaluate your solution. Make sure that, you have a hold offset. Again, for machine learning people, this is obvious, but actually for systems, people actually overfit. They have a bunch, when they publish papers, what they actually have one benchmark, which they try to maximize the numbers for that benchmark, right? Need to use diverse workloads, of course, to provide overfitting and hold out data sets. And the final one, which is very, very serious, is prevent reward hacking. Here you have to be very careful. When you tell someone to a human to do, there is some context of what is reasonable and what is not reasonable. You don't bother to say, you don't even think about it. But these LLMs are very smart. If you don't tell them something, they are going to exploit it. There are things like in our EPLB, they are going to drop tokens, right? And report much better numbers, right? Because it drops the tokens. This is another one. Like I said, it's like in terms of the workload, some of the experts requires a fraction of the GPU, right? They don't require the entire GPU. So what they do when they do the math, in that case, they use integer. So they do division, and the division is going to be integer division, and it's 0. So 97% of the experts are 0. So they balance only 3% of the experts, and obviously be super fast, right? Or this Cloudcast was moving the data across efficiently about different regions in different clouds, right? And how do you reduce the cost and how do you reduce latency? They kind of change the file sizes when they transfer it, right? So this is what I'm saying. If you don't think about this, but so you really need to be very careful. Comprehensive tests are the way to go. There are different things like constrain the number of line changes, right? This is similar with scale, divergence, penalty, and RL, right? The other thing was very interesting. Like here it is. You generate the code, and the code has error, doesn't compile, so forth. What do you do? In the first iteration what we did, we say, forget about it. But it turns out that's not the best thing to do. Maybe you want to add to this kind of compose course with a very small weight. Why? Because the code, despite the fact it didn't compile, actually may have good ideas in it, and you want to use those, okay? So I think that's another things we discover. Now, you may think about, and when I talk with, especially maybe you are convinced you are, like this is a great idea or whatever. But when you think with talk with the system people, they say, okay, because, why this should work? I mean, I work in systems for a long time. I know all the techniques. Why should they do better than me? Maybe they do better for, first year students because they don't know everything what I know. But actually, there are a few reasons. First of all, why this optimizing problems domain is that it's easier to verify the correctness, right? Than, writing the entire system from the ground up. Because when you optimize something, the optimization shouldn't change the semantics of the system, what the system is doing. But anyway, now let me go back to why is that I think that this address is going to work. There are two reasons why, and better than humans. First of all, is very prosaic. When you are a student and even an engineer, what do? You are going to do something, and you are going to stop. You are going to develop the solution. You are going to stop when things are good enough, right? Right. I want to write a paper. It's 10% better, or whatever the standard for that problem it is about what is publishable, right? You stop and you publish. These things never stop unless they exhaust the budget, right? But the second one, the second reason is more profound. In many cases, when you solve a problem, you apply techniques from one domain to another domain. And here where the LLMs have an advantage over all of us, because they are trained on all the publication, everything from all domains. We are pretty narrow, right? When you become experts, the definition almost of experts, you are going to know more and more and more about your domain. Domain expert, that's why they call us. And here actually some data points, right? These are some examples in which the solutions borrow some techniques from different disciplines, like political science, welfare economics, electrical engineering. You may say, yeah, this is closer to CS, but still, for most people, it's still far away. So I think that kind of makes it quite exciting. Research challenges, and I'm going to have a few more minutes. The good evaluators are the key. That should be, this is where you should spend your time, right? And need to be fast and faithful and obviously correct. It has to be fast because it's an iterative process. And it's going to have a few hundreds of iterations and may feel low number of iterations, but if each of these tests is going to take a few hours, that's mass. It can be mass. And here there are many ways you can do it. Problem-specific simulators, maybe, to make it fast. Cascading evaluators, you can have different levels like model evaluators, parameterized models, simulators, and then all the way to emulation, all the way to the real system. Or use formal specification. And obviously the other exciting thing that I'm going to talk about is go beyond system performance and the search, efficient search, right? Because you want to have fewer as possible iterations to find the solution. So where does this leave us? So I think the way to, what is exciting is that for me, it's like this will be great for research because hopefully it will elevate every researcher. And instead of spending your time on developing solutions, you are going to spend more time of selecting which problem to solve, okay? And formulating the problem evaluation strategies. You are going to become, everyone is going to become more of an advisor, right? This is what advisors do, right? It's like, in some sense. So I think, and the things about this is I want to make sure, and you see that appearing also being more and more prevalent, also some of these code assistants, is the mode of working is asynchronous. And I think this will be the future, right? It's not necessarily interactive. Why? Because the human's bandwidth is going to become, time is going to become the bottleneck. If it's asynchronous, you can do, you can spend more time. Okay, this is a problem, go work on it, come back with a sample solution. Oh, this is a solution, tell me why is that, and so forth. Hey, here, try this next, right? So you can work with many of these things at the same time, like an advisor can work with more students. If you do this kind of more interactive way, like with some code assistants, it's more like peer programming, right? So you work with only one. Okay, so one last thought, and why I think this is very exciting. I think that is the right time, and actually we have to, this technique, you need these techniques, are necessary to make progress and to solve some real problem we have today. And basically here, the software stack we have today in AI is so complex, which I believe that humans, we cannot keep up with the complexity and iterating on it. And just to give a sense, so in 2010, Reza knows very well those times with Spark and so forth. It was a complex workload, much more complex than other workloads. But if you think about it, it was a big data processing, was homogeneous, it's bulk synchronous processing, very regular, right? And the systems you are running on, it was also distributed, and at that time it was very large, but it was very homogeneous. It was just servers, x86 servers, with each of them with some disk attached to it, connected by Ethernet networks. And that was pretty much it, right? And if you look fast forward today, if you look about this kind of compute substrate, it's crazy how complicated it is, right? You have accelerators. Not like in terms of accelerator, we have this other project, VLLM, the inference engine. And they look at September last year, I have the number, I am trying to get the number today. It was supporting 260 different accelerators, okay? And it's not only different accelerator, you have different network technologies, right? And then you have now different, packaging, right? You have rack scale accelerators like NNBL 72 or cluster level like pods. The workloads are far more complicated. It's not the data processing, it's also now you have post-training. If you look about like inference and training, inference, do you know how many parallel strategies you need to kind of juggle? Over 7 type of parallels. And it's not like they are hierarchical, they are operating kind of many of them at time scale, at the same time scale, right? The inference engine is kind of, it's distributed, right? Disaggregate pre-fill. Like I told you, I shown you is expert parallelism and so forth, and many other techniques which are invented every time, every day. So what I'm trying to say, this is a very, very complex environment, very, very complex hardware, right? Environment and very complex workloads. And on top of that, things are moving very fast, okay? So every year you have a new version of a GPU. Think about NVIDIA, right? Now it was announced Vera Rubin. And it's not like x86, which you basically have the same, more or less, instruction set. The new chips have new instructions. Add new instruction. Why? Because they want to be faster and they are going to specialize now new operations in silicon and provide you the instruction to be able to access that functionality. Okay? So I'm telling you, like, for instance, okay, and like with VLLM, it's like we barely are kind of optimized. I asked people like the other day, are we still having really optimized for B200? And they say, yeah, maybe you are close. And Vera Rubin was announced. It's not, and you say, oh, but it's outside NVIDIA. No, NVIDIA software people have the same problems. I talked with someone who is trying to do these compilers, right? It's the same thing, right? You have other third parties who actually are faster than Nickel. Why they are faster than Nickel, which is their communication library, collective communication library? Because they use these new instructions for communications and doing some aggregation in chip aggregation and so forth, and which Nickel doesn't do yet, right? And finally, it's about cross-layer optimization. The way we conquer the complexity in systems, the traditional way, you do layering, like internet, right? 5 layers or whatever. And with the system, everything is a modularity, right? Barbara Liskov from MIT a few years back got the Nobel Prize for that, right? And this is how we design the systems, right? Modular systems, microservices, everything. But this one is very hard because performance, before we can say, okay, this is a few percent slower, but it's very modular, evolvable, and so forth. You cannot do that now because it costs you, these workloads can hundreds of millions of dollars or billions of dollars. So 1% is tens of millions, okay? So it's not acceptable. So what they do? They break the layering. So all of this together, I think that increases at least one order, maybe two order of magnitude, the complexity of building these stacks, right? And I don't think that we are in the position with that to do it, just as a humans. And I do think that this is a real opportunity to use these tools to really make a difference, right? And in process, you can do a little bit of this flywheel. You can use AI to build better system to build better AI. Okay, so in summary, I think we have enough evidence. I think that now the system research will be changed forever by these tools. Why? Because we already have SOTA solution on several problems. There are many, many questions, open questions. How can you use these tools effectively? How can you make these tools even more effective, right? Okay, more explainable and so forth. Because you think about when you have like this advisor, when we talk about the advisor student, when you meet an advisor and you meet your employee, you have like junior engineer, he's not asking, oh, what you've done, what is the solution? Then you start to ask questions. Why did you do that? Tell me more, right? So this kind of, it's not going to be easy. The explainability is going to be very important. And we have to focus more on the problems instead of solutions. And fundamentally, we need ourselves to learn how to keep up with these changes, which will only accelerate. But again, the world is extreme, the present and the future are very exciting. Thank you. I think the question is what is good enough, right? And that will depend on your application, right? I think, and I do think that this is another theme. If you look about the AI, I think that the biggest challenge of AI today, from my perspective, is reliability, right? Because if you don't have things working reliably, it's, you are not going to trust them. So, and the higher value for your applications, the higher the value the application has, the more reliable it has to be. But it's going to be case by case, right? Because, and you see, at the end of the day, when you use these tools, you are still liable, right? So it's whatever you're comfortable with, right? And again, you can do many things. You can do this. You can do other models to check the results from the model, from the solution. You can have this kind of almost like actor critic, right? And provide feedback, right? Many things you can do. Right? What I like about this kind of things, about OpenEvolve and these things, it's actually pretty simple. It's like a few hundred lines of code. And again, the more complex something is the harder to understand, evolve, and control.
Have you tried using AI to write the reward function?
Reward function?
Yeah.
Reward function? So in this case, the reward function is a score. Right? Actually, let me make it's a very good point. So in this case, what OpenEvolve and others do is they combine. If you have like two metrics, they combine some weighted average. It's called combined score. For Japa, you are going to hear from Atay later. It's some of the work we've done. You can have multiple scores, and you can try to treat them independently and to advance the Pareto frontier. But let me make one comment here, because I think it's very important. Because these systems, one thing is about how do they compare with RL, right? Because for the longest time, we applied RL to systems to come up with new kind of solution and things like that. So in both, at the high level, there is some similarity. In both cases, you have a prompt. You have a model, you have a policy, and you feed the prompt to the model to get a solution, and then you evaluate it, right? In this case, with RL, you have rollouts, right? And you get the feedback, and you iterate. The differences are, with RL, you update the policy. With these systems, you update the prompt by adding, for instance, more previous solutions and things like that, right? Having a little bit of the prompt history. So that's one. But and these are there are a few a few things which matters. One thing which is very important is that the feedback for RL, you have at the end of the day all that feedback to narrow it down to some numbers. Why numbers? Because you are going to update a policy. You are going to update the policy, you would use HGD, so you need to have some loss, right? So in the process, you are going to lose a lot of information. Here, the feedback is very rich. It's not only the score, this is a solution which provides that score. These are errors, if there are errors. You can provide traces and so forth. So you have a much richer information, right? I think that's very important. So that's why it's not kind of reward function, you need to be careful in what you are going to provide, but it's also very important for the iteration process, what other information you are going to provide. Because in this case, you can, right? And the other thing which is very important here for this one, which makes them very, I think in my view, is that the solution which you are given, it's explainable. With RL, it's a policy. It's a batch of weights. It's harder to figure, to get a good intuition of what's happening. But here, you kind of read the code, right? And I think this makes it also much easier for the human to be in the loop, right? Because you understand the intermediate solution, then you can provide more hints or something like that. So I think these are the two key differences which makes me pretty optimistic about this direction.
Yeah, same. Code is very verifiable, and systems are code. So it's incredibly exciting time to be in this. So let's thank Jan one more time.